So imagine locking 35 elite mathematical minds inside the Max Planck Institute in Leipzig. Their sole objective is to, engineer a test so rigorously complex and so steeped in novel abstraction that no artificial intelligence could possibly cheat its way through it.
Right, a completely adversarial benchmark.
Exactly. So they spend weeks crafting these problems, they finalize the gauntlet, and then they let the AI take the test. But before the AI even answers, it pauses, looks at the exam, and points out that the human mathematicians actually got their own math wrong. Welcome to the deep dive.
It really sounds like science fiction, but that is the reality we are analyzing today.
Yeah.
The June 2026 paper, Benchmarks in Leipzig, documents exactly this phenomenon. And it touches on a crisis that anyone working in machine learning evaluation is currently facing, which is, the ultimate contamination problem.
Oh, absolutely. I mean, if you are building evaluation pipelines for your own models right now, you know this nightmare intimately. How do you test a large language model for genuine zero-shot deductive reasoning when you know its training data likely contains, well, the vast majority of published mathematical knowledge in human history?
You are constantly second-guessing it.
Right. You are constantly wondering if you are measuring an actual leap of logic or just a highly sophisticated, high-dimensional data retrieval process just because the model memorized some obscure ARC's fifth paper from 2019.
Which is the exact tension this group of 49 mathematicians, 35 in person at Max Planck, and 14 dialing in remotely attempted to resolve.
And this was between April and May of 2026, right?
Exactly. Their mission was to construct a dataset of 100 research-level mathematics questions, but the requirement was that the underlying frameworks had to be public.
Because a model cannot reason about a definition it has never seen before.
Right, exactly. But the deductive steps to reach the answer had to be entirely novel. So the goal of our deep dive today is to really tear apart the methodology behind this benchmark. We need to look at the three-stage evaluation gauntlet the researchers built and severely scrutinize the empirical findings.
And we really need to dig into those findings, because the data they pulled out of this experiment exposes some massive architectural quirks in current LLMs.
Yes, specifically regarding intra-model variance, the mechanics of test time compute, and, frankly, where the absolute ceiling of AI reasoning sits today.
Well, to really grasp the weight of the performance data, we kind of have to start with the constraints placed on the human authors.
The submission rules.
Yeah. They utilized a submission platform called ScienceBench, and the inclusion rules were draconian by design. Every single question had to possess a unique, well-defined, and completely unguessable answer.
I want to pause on that word for a second, unguessable.
Sure.
Because in higher mathematics, depending on the subfield, questions often naturally collapse into a very small set of plausible integer answers.
Right, like 0, 1, or -1.
Yeah. So a model could hallucinate the entire proof, guess one, and get a false positive for reasoning.
And the authors noted that mitigating that was a massive headache for them. They explicitly banned proofs or simple, necessary, or sufficient conditions as answers.
So what did the answers have to look like?
The outputs had to be concrete and complex. So like a specific multivariable polynomial or a counting function with highly constrained parameters, or even a hyperspecific rational number.
Okay, wow.
They were targeting the latent space of published research. Think of a scenario where an author derives a lengthy, complex, edge case example during their research, but leaves it out of the final published manuscript due to space constraints.
Ah, I see.
That unpublished derivation is the target zone.
But wait, if they are pushing for that level of complexity, how do you prevent the human authors from just creating questions that are functionally, computational black holes?
What do you mean?
Where the model fails not because it can't reason, but because it just can't compute a million by million matrix in its head.
Oh, right. Well, they instituted a rule that complexity could not arise solely from computational heavy lifting. While human authors were allowed to use computer algebra systems to verify their own submissions, the core obstacle for the LLM had to be structural logic.
Okay, that makes sense.
To enforce this, ScienceBench employed a strict three-stage submission workflow. They called it W1 through W3. In W1, the mathematician inputs the question and the final answer.
But not the steps to get there.
Right. The models don't see the steps.
Yeah.
Then, in stage W2, 5 active frontier models, GPT 5.5, Gemini 3.1 Pro, Claude Opus 4.7, DeepSeek V4 Pro, and Grok 4.3 are given the question.
And they just see how they do.
Yeah, but here is the filter. A question only survived to be included in the benchmark if 3 or fewer of those 5 models could solve it.
Wow, that is a brutal filter.
It really is.
If 4 models solve it, the question is deemed too trivial and thrown in the trash. So you are actively selecting for the bleeding edge of failure.
Exactly. And then comes W3. Only after the question passes that W2 filter does the human author provide a private, completely worked-out solution and the relevant references.
So they have to prove their own work.
Yeah. This final stage forces the human experts to rigorously clarify their own deductive logic, ensuring the problem is actually solvable without leaps of faith.
And what was the final breakdown of the benchmark?
The resulting distribution is staggering. Out of the 100 surviving questions, 36 were in algebraic geometry, 22 in algebraic combinatorics, 18 in matroid theory, trickling down into incredibly dense fields like knot theory and arithmetic geometry.
Okay, this brings me to a structural flaw that immediately jumps out to me.
Let's hear it.
If these humans are designing unguessable, deeply adversarial problems specifically meant to break AI, how do we know the humans didn't just make a mistake? I mean, human error in pure mathematics happens all the time.
All the time.
So if the benchmark is flawed, the AI's failure is completely meaningless.
That intuition points directly to the post-collection audit phase, which the researchers labeled A1 through A3. And this is where the paper delivers a profound shock to the system.
Oh, this is the peer review plot twist.
Yes. To audit the benchmark, the researchers used an AI-assisted review process. The LLMs were tasked with reviewing the human submissions for typos, missing assumptions, and structural reasoning errors.
And this is where the AI flags the humans.
It is.
Isn't it?
16% of the benchmark was flagged for potential mathematical issues, and these were not AI hallucinations either.
Wait, 16%?
Yeah. This feedback loop actually triggered direct personal email exchanges with the contributing mathematicians.
I can imagine those emails were pretty humbling.
Probably. The result was that 12 questions had to have their formulations formally updated. 3 questions were so fundamentally broken in their premise that they were outright removed from the benchmark.
Wow.
And most surprisingly, several elite authors had to correct their original human-derived answers to match the output generated by GPT 5.5 Pro.
That is incredible. The ruler they built to measure the AI's flaws was actively calibrated by the AI itself.
Yeah.
The models being tested actually corrected the human experts designing the test.
And we are seeing this across the broader machine learning landscape right now. The Leipzig authors contextualized their findings by comparing them to Epoch AI's Frontier Math project, which launched around the same time.
Right, I remember that one.
Epoch AI had to publicly announce that an AI-assisted review of their own Tier 1 through Tier 4 problems flagged fatal errors in roughly a third of their human-crafted questions.
A third. If you are an ML engineer listening to this, the implication is massive. It demonstrates the immediate practical utility of LLMs, not just as answer engines, but as tireless, highly pedantic peer review sounding boards for high-level mathematical content.
They are fundamentally changing the workflow of pure mathematics.
Oh, totally. So with the benchmark finalized and verified, the researchers moved to the empirical evaluation. And the data from stages 1 and 2 of the gauntlet uncovers a severe variance problem inherent in current ML architectures.
Yes, but before we look at the solve rates, there is a critical engineering detail regarding the test environment. Web search, code execution, and external computation tools were explicitly disabled.
Wait, why turn off the calculator? If the goal is to evaluate if an AI can do math, why strip away the tools it naturally uses to execute math?
Because the researchers discovered in earlier trial runs that when those tools were enabled, the models just abandoned abstract reasoning entirely.
Oh, really?
Yeah, they defaulted to brute force algorithmic approaches. There is a fascinating quote from a GPT 5.5 chain of thought log where the model explicitly states, quote, "I'll translate your question into the framework, then compute the answer exactly rather than doing simulation."
So it's just trying to crunch it.
Exactly. It would try to write Python scripts to crunch the numbers. So, by disabling code execution, the researchers forced the models to navigate the abstract latent space symbolically. They had to hold the abstractions in their weights rather than offloading the state to a Python runtime.
They forced the model to think rather than just compile.
Got it. So what happened in stage 1? Stage 1 was a single attempt run, a straight zero-shot query. The results showed GPT 5.5 leading with 44 out of 100 questions solved.
Okay, not bad.
Gemini 3.1 Pro solved 15, Claude Opus 4.7 solved 13, DeepSeek V4 Pro solved 10, and Grok 4.3 solved 6. After just one attempt, 41 questions remain completely unsolved by any model.
Which seems somewhat low for models of this caliber, honestly. But I mean, a single zero-shot attempt is a terrible way to measure the latent capability of an autoregressive model.
Why do you say that?
Well, if I ask you a complex question and demand the first thought that comes into your head, your failure doesn't mean you lack the knowledge. It just means that specific retrieval path failed in that exact millisecond.
Which is exactly why Stage 2 was necessary. The researchers partnered with Surge AI to query each model 20 times per question.
Okay, that makes much more sense.
This methodology separates two vital metrics that every data scientist should care about: solve questions, which means the model found the correct answer at least once in 20 tries, and the correct run rate, which measures the overall reliability across all attempts.
And the contrast in those two metrics is where the architectural quirks really show up, right?
Oh, definitely.
Let's look at Claude Opus 4.7. Across 20 runs, it managed to solve 44 questions at least once, but its correct run rate was only 15%.
Right.
There were 19 different questions that it solved, but in no more than 3 out of its 20 attempts.
Meanwhile, GPT 5.5 solved 75 questions overall, with a much more stable 52% correct run rate.
So Claude Opus 4.7 clearly has the latent knowledge baked into its weights, otherwise it wouldn't have found the answer at all, but a 15% reliability rate?
It's erratic.
Yeah, it feels less like a deterministic reasoning engine and more like trying to balance a pencil on its tip in a windstorm. It has the coordinates of the knowledge, but it just can't stay upright. Why is the intramodel variance so violently high?
To understand that, we have to look at the mechanics of autoregressive token generation. When an LLM generates a chain of thought for a mathematical proof, it is calculating the probability distribution for the very next token over and over again.
Right.
If a proof requires 100 logical steps and each step requires 20 tokens, you are generating 2,000 tokens in a sequence. Even if the model has a 99% probability of selecting the optimal token at every single step, the cumulative probability of a perfect sequence degrades exponentially.
Because you are multiplying 0.99 by itself 2,000 times.
Yes. In pure mathematics, one slightly suboptimal token choice at step 4, maybe it uses the word assume instead of let, can subtly alter the context window.
And that just spirals.
Exactly. By step 80, that slight deviation in the probability tree has compounded into a massive hallucination. The model takes a wrong branch in the logical tree, and because it cannot natively backtrack in a standard zero-shot generation, the entire deduction collapses.
So the high gap between solved questions and correct runs proves the models possess the requisite logic steps.
Yes.
But traversing that exact path continuously without hallucinating remains statistically fragile without scaling compute.
That's the core issue.
So even with 20 attempts per model in Stage 2, the combined efforts of all 5 frontier models left 16 questions completely untouched. Nobody got them right even once.
Right.
Which forces the researchers into Stage 3. Because if the bottleneck is sampling variance, if the model just keeps taking the wrong branch in the probability tree, you need a mechanism that allows the model to explore those branches internally before it gives you the final answer.
Exactly. Stage 3 introduces inference time scaling, utilizing models specifically engineered for what we call test time compute. The researchers took the 100 questions and ran them 3 times through GPT 5.5 Pro with extended thinking enabled and Gemini 3.1 Pro depth think.
I want to make sure I really understand the mechanism here. When we say extended thinking or deep think at inference time, how is that fundamentally different from what Surge AI did in Stage 2?
Good question.
Isn't the model just trying 20 times implicitly and hiding the failures from me?
No, it is a vastly different architectural approach. In Stage 2, Surge AI was just running independent zero-shot generations. It rolls the die 20 separate times from the starting line.
Okay.
Test time compute models, however, are essentially performing a hidden search algorithm like Monte Carlo tree search over the reasoning steps themselves.
Oh, interesting.
They generate a partial chain of thought, evaluate if it is leading toward a contradiction, and if so, they backtrack and explore a different branch of the probability tree before outputting the final sequence to the user.
That makes sense.
It is dynamically allocating computation to verify its own logic step by step.
It's internally checking its work against the latent space constraints. And the jump in performance when you enable that mechanism is staggering.
It really is.
GPT 5.5 Pro with extended thinking rocketed up to 88 solves questions. And its consistency problem evaporated. It achieved a 79% correct run rate across its 3 attempts.
Yeah, in fact, 69 of those questions were solved perfectly every single time.
That's wild. What about Gemini?
Gemini 3.1 Pro DeepThink also saw massive gains, reaching 56 solved questions. But what is particularly interesting for ML researchers is the divergence in their latent representations.
How so?
Well, GPT 5.5 Pro solved 36 questions that Gemini missed entirely, while Gemini solved 4 questions that GPT 5.5 Pro missed.
Oh, wow. So they are employing different search heuristics through the mathematical latent space. But the ultimate takeaway from stage 3 is the sheer attrition rate of the benchmark itself. By the end of this entire gauntlet, after the 20-run sampling and the inference time scaling, out of 100 adversarial, heavily vetted, research-level mathematical questions, right, out of all those, only 2 remain completely unsolved by any model.
That's right, question 099 and question 100.
Let's give our listeners a taste of what the absolute bleeding edge of AI failure looks like today. For those of us who spend more time in PyTorch than in abstract algebra, what exactly are these 2 unsolved problems demanding from the model?
Sure. Question 099 involves calculating representations of a 4-vertex quiver.
Okay.
The prompt asks the model to count all the unique lunotypes for representations of the quiver of a specific dimension vector across all stability conditions that admit semistables.
I'm already lost. What does that mean structurally?
Structurally, a quiver is essentially a directed graph. But to solve this, the model cannot just trace a path. The constraints of calculating stability conditions require the transformer to hold multiple competing abstract states in its context window simultaneously, mapping nonlinear geometric invariants.
Yeah.
It just overwhelms the model's abstract working memory.
So it's not a failure of knowledge, it's a failure of multidimensional state tracking.
Yes, exactly.
And question 100.
Question 100 asks for the asymptotic maximum density of triples shattered by a set of 6 permutations of size n, such that the identity and the reverse permutation are elements of the set.
Okay, that sounds just as complex.
This is deep algebraic combinatorics. It requires a synthesis of asymptotic analysis and permutation group theory that essentially demands a novel, multi-step proof framework that doesn't cleanly map to any single methodology in the training data.
We've reached a point where we are no longer testing if AI can do math. We are using these models as instruments to map the exact boundary conditions of their own abstraction limits.
Yeah, which brings us to the paper's ultimate conclusion, and it is a massive disruption for the academic community.
Let's hear it.
The authors state it clearly. The era of writing exercise-style benchmark questions based on publicly accessible research is ending for frontier models.
Meaning, human experts are losing the ability to design tests that the AI will fail unless they completely abandon public knowledge and start testing on private, unpublished data.
Exactly. The model's capacity to synthesize published mathematical frameworks has become so comprehensive, and their inference time reasoning so robust that constructing a problem they cannot solve while adhering to the rule of only using published literature is practically impossible.
That's amazing.
The benchmark methodology itself is buckling under the weight of the model's compute capabilities.
So if you are an ML professional, a data scientist, or a mathematician navigating this space right now, Benchmarks in Leipzig forces a total recalibration of how we view the intersection of machine learning and formal mathematics.
It really does. The barrier to solving complex mathematics is no longer the deductive execution.
Right. The models can navigate the probability trees, they can backtrack, they can synthesize the latent space. The barrier is shifting toward the formulation of the problem itself.
We are seeing the transition of the LLM from a fragile high-variance generation engine into a highly reliable, inference-scaled reasoning agent. The fact that they are already being utilized to correct the human mathematicians who build their evaluations is proof that their role has permanently changed.
Absolutely.
Which leaves us with a profound forward-looking thought for you to mull over. If an artificial intelligence can reliably untangle, internally verify, and solve 98 out of 100 heavily vetted, unguessable, adversarial research-level questions derived from published papers, how soon until the definition of mathematical research shifts entirely?
It's a valid question.
If the machine becomes functionally flawless at the mechanical act of finding the answer, does the value of the human mathematician transition purely to the creative act of defining the right question? It's something to think about the next time you're building an evaluation pipeline. Thanks for joining us on The Deep Dive.